to Woofferton transmitting station near Ludlow in England on this fine and sunny day. It's a change, it's not raining. My name's Dave. I'm a transmitter engineer at this site. If you just look round, you can see the satellite dishes behind me from which we obtain all the feeds for the shortwave services that are broadcast from here. Further in the background are the shortwave antenna arrays, and the site covers about 320 acres. The site was obtained in 1943 and was built by the BBC as Woofferton transmitting station, but they didn't call it that to start with. It was called Overseas Station Extension number 10, OSE 10, and it was the last one of the Aussies, as they were called, that were built. It kept the name Aussie 10 until about 1960, when it became again Woofferton transmitting station. When the station was first built, it was equipped with 6 RCA 50 kilowatt shortwave transmitters that came across from the States on lease lend and were installed in the building. So the total power output of the station was about 300 kilowatts, 6 by 50. That situation continued until 1963, when by then the Americans had taken an interest in this site. Actually, they started in 1948 and used 4 or 6 of the RCAs as the VOA, the Voice of America relay station in the United Kingdom. They carried on like that until 1960, when they was almost going to shut the station. But then the fiasco in Cuba arose, and the Voice of America realised they needed more power to get their message to the Soviet Union. So they decided to upgrade Woofferton as their relay station, and they had it equipped in 1963 with 6 250 kilowatt shortwave transmitters made by Marconi, and this was the first site that these transmitters were ever installed, and we'll go and look at those in a little while. So that gives you a rough idea of their progress until about 1963. The Cold War continued, and by 1979 President Reagan was in a spending mood, and he decided to invest more money in the Voice of America. So they decided to remove the 2 remaining RCA 50 kilowatt transmitters that were not in use. They were just down the end of the building. They removed the 2 of those and installed 4 300 kilowatt Marconi automatic type transmitters, and they're still in use today. We'll go and look at those in a little while. And that's how it continued with 10 effective 250 stroke 300 kilowatt transmitters. So the station from 1979 to the year 2005 was pretty well equipped with 10 300 250 kilowatt transmitters, and that was the mainstay of the system. Okay, so let's now get inside the building and show you what happens in there. I've come to this door a good few times since I arrived here in December 1982, and I've stayed for, that's quite frightening, almost 30 years before finally walking out of the door. But anyway, off we go. First thing to see in here is the Great Circle map. Many of you will be familiar with one of these. From the UK, it's centred on London, and you can see that New Zealand is not quite as it would appear on a flat map, and Australia doesn't quite look the same, but Africa is fairly well defined, as is South America and North America. As you see, London's the centre, and we've just popped 3 bearings on there, just one of the arrays outside. It's a 21 megahertz array we've illustrated, and it just shows you the countries that you can cover on the beams that you can send out from the array. The normal array will be 114 degrees, but we're able to move it 12 degrees to 102 and 12 degrees to 126. So we can start to cover different countries. You can see the Horn of Africa on 126, and you can see as we go down on 114 it goes through Albania and then almost onto Mecca. 102 degrees, popular bearing these days for shortwave broadcasting, is towards Baghdad and Tehran. So you can see the 3 slews there. This array that we're talking about was a 21 megahertz array, and it also will slew backwards. It will reverse, so you can cover different parts of the United States. You can the central part here, Central America's there, and then the mid states, and then over to the north coast, or the west coast, the northwest coast. So a very versatile set of bearings there for that particular shortwave array. I'll just stop and look at these few photographs. of Woofferton by night on the satellite farm, or by evening sunset I should say. Then Woofferton in the flood. The actual station is on a flood plain almost, and the water is only ever about 300 millimetres below the surface, and often will appear on the surface. This makes it a great site for shortwave broadcasting. So Woofferton in flood. Woofferton in the winter, you can see the hoarfrost on the arrays and on the tree, and the RF switch stations there that switch the different antennas to the different transmitter outputs. Woofferton in the fog, and the final picture is Woofferton as it was after 1979 up to about 2005, with the 6 250 kilowatt Marconi transmitters towards us, and in the rear hall, not terribly well lit there, are the 300 kilowatt Marconi transmitters. Right, let's go through into the hall, which doesn't look the same as that now. That's because there was an upgrade in the year 2005, where the first one of the Marconi 250 kilowatt transmitters was removed and replaced by a unit from Croatia made by RIZ, Radio Industries Zagreb. It was a 500 kilowatt transmitter, far too powerful for the arrays that we have here. So the company asked that it be downsized to 250 kilowatts, and that's what was done. That was the first one that was placed, but unlike any of the previous installations, it was placed in a fire cell. This was the modern technique, and it's done to prevent any damage to the rest of the building should a catastrophic fault occur on the transmitter and it does burst into flames. The modernisation continued with, that was sender 96 that was first removed. Sender 94 was taken out afterwards. Then sender 92, which is to my right here, and the latter one that was taken out was sender 91. That left us with 2 of the 1963 senders, sender 93 and sender 95. So these are the fire cells. We'll just walk past. We're going to look at the vintage sender 93 first. It's sender 95, one of the senders that were installed in 1963. Its brother next door, sender 93, was the prototype. We're going to have a look at that one in a moment with all the doors open. But first, just to give you an impression of the 3 units here that make a 250 kilowatt shortwave sender, let's just have a look at the first one. This is the main RF unit, radio frequency unit. Metering on the front, handles on the front for manual tuning. These senders are manually operated and manually tuned. Comprehensive metering here of what we need to see when you're using a broadcast transmitter. In a little while we'll switch this on and you'll be able to see it all work. But just to look at it cold, we've got unbalanced power, penultimate anode current, we'll look at that. VSWR, a term with which many of you will be familiar. Final anode current, balanced power for the output. Then you've got the metering of the 4 tubes or the 4 valves in the transmitter. There's a pen RF stage here and a final RF stage here. Power comes in at about 5 kilowatts. We generate 5 kilowatts of carrier and feed it to these pen tubes. They're grounded grid, so very stable. We tune the anode with the white handles. We tune the cathodes of the next stage, the final stage, with the green handles. And we tune the output anode circuit of the final stage with the orange handles. We can alter the power that goes up and down. We can alter the power that goes out to the array by up and down by the 2 knobs there. And there's metering of various voltages on the filaments of the tubes. That's the RF section. I told you about we need 5 kilowatts of drive. Marconis were always very savvy. They wanted 5 kilowatts. They'd see what they got in their shop, and what they had was a 5 kilowatt amplifier. This is the H1100. Absolutely bog standard RF amplifier, much used by the military. 1 tube in the output, a wideband valve amplifier, and now a synthesizer from which we can generate the frequencies that we need. This one you can see is set to 13.7 megahertz. Manually operated, tuned, tune and load, plate tune, plate load. Quite standard design. As I say, up to 5 kilowatts out. This unit was available in various versions of AM. You could have an amplitude modulator with it if you wished. You could have it frequency shift keyed. You could CW it, as we do here. Or you could use it on FM with various options. But obviously this was the basic carrier only 5 kilowatt option. So that's the H1100 air cooled. Let's go through and look at the other bit. The RF section, as you know, generates 250 kilowatts of carrier. To become a broadcast station though, you do need something more than that, and you do need modulation, you do need program input on the carrier. This is the modulator, high level, class B. So you're looking at a valve modulator here to generate about 180,000 watts of audio. I'll say that again, 180,000 watts of audio. They take the advantage here of using the away from the RF to make the modulator the control department, where you can switch the sender on and off, you can meter various voltages, as well as being an audio amplifier. In addition, we've removed the cathode ray oscilloscope that was used for waveform monitoring and replaced it with the industry standard Orban HF processing unit. Within here are the settings that are required to make it punchy audio and to give the sound that we want on shortwave to break through the interference and static, etc. So that's the Orban. This is on sender 93. We've looked at sender 95 complete. This is sender 93 with the doors open. So, sender 93's RF output appears on the coax at the top. It's not coax like you'd expect at home. It's rigid aluminium inner, or copper inner and aluminium outer. And the 5 kilowatts goes along the coax and appears into the top of the sender, where it goes downwards and enters into a ferrite balun. This is located deep in the bowels of the sender and is a devil to change if it goes faulty. So let's go around the corner now and look at the pen RF stage, and then we'll work our way through onto this side, onto the final RF stage, and then we'll look at the power output at the top there. So let's go around the corner. Yeah, the RF comes in on the coax, hits the balun, and then is split between the two tubes. Here's one of the tubes here, and the other one is behind. They're both ceramic bodied ones. You can see the white pot finish. Marconi's described the wave change procedure for these transmitters as that you remove the plug-in coils. Here's an example of one of the plug-in coils. Plug in. Goodness me, I need to get stronger. There we are. This is the plug-in coil, and out it comes. See, it's got a locating peg here, and a set of them are available for all the different frequencies or the wave bands that we use. This is 17 megahertz and 15 megahertz. I just slots it, and away we go. The coils were not made by Marconi's themselves. We understand that they were made by a firm in the UK called Boozy and Hawkes. And to anybody that plays a trombone or other brass musical instruments, that's often the source of such an instrument, is Boozy and Hawkes. So they're into making tons of coil. Here on the pen stage you can see the way that the filament supply is routed through the Pyro-Tanax feed choke, and there are some suppression resistors on there, so the fills are routed down there. The reason for that is that the RF is fed into the cathodes of the valves, and you don't want the RF to go down the cathode, down the filament supply. You want it to go into the filament itself, into the cathode. So you have to have an RF choke to prevent that happening, and there it is. As I say, the grid's grounded here, and the anode, here's the boiler in which the anode sits of this tube, steam cooled. So the water, this deionized water, comes up through the white pipe into the bottom of the boiler, overflows a weir, and the steam and excess water go off down this glass tube for insulation, and all that lot's taken down the back and then condensed. So that's how that works. That's absolutely standard vapor cooling. Very efficient, because of course you take the water from water into steam, which takes a lot of heat away. This peculiar thing here is a fixed capacitor, value of 1000 picofarads, glass, made by Jennings in 1963. It's one we haven't broken. You can see the large transformers underneath to supply the current for the tubes. Okay, so out the anode via that capacitor, and we hit the fills again via this coil, another plug-in coil. We hit the fills of the output stage, and if we just look below, you'll see the large boiler within which the BY1144 output tube is mounted. These two plates here, nice smooth edges here to prevent any RF, to prevent voltage flashover, high voltage flashover. These have got two resistors mounted. That's copper at the top on the boiler, and that's copper at the bottom on the boiler. And across that are two 68 ohm resistors to stabilise that stage. It looks weird that you've got copper and resistors, but it does work. You can see a much larger steam pipe to the right hand side. And of course the ceramic on these output tubes is much larger than on the pen stage. The pen stage gives about 40 to 50 kilowatts output. These tubes give 125 kilowatts each. So it's a much larger tube. The fill supplies are much more comprehensive. So you've got 4 chokes for 2 tubes. Here's one of them. The one there. Within the tube are 2 separate filaments to 325 amps at 9 volts on each one. And there's the connections to one set of the filaments, and off it goes into the valve. Okay, that's the RF stage from the drive stage. Let's go have a look at the RF stage from the output. Okay, well here we are in the RF section. This is the actual output stage of the sender. You can see the 2 RF tubes mounted in the boilers. Again, they've got the water pipes below, just like on the pen stage. And different here, of course, in that you've got one of the output coils. This is a 15 megahertz output coil, also works on 13 megahertz, which corresponds with the frequency on the synthesizer that you've just seen. 13 megahertz coil. The HT, the high voltage, modulated high voltage, comes from an enclosure at the rear called the modulation enclosure, and it appears at the center tap here through this little bit of parasitic stopper, and then onto the center of the coil. So that's onto one anode, one plate, and that's onto the other plate. That is tuned by 2 capacitors underneath, vacuum variable ones, that will work from the handles at the front and resonates at 15 or 17 or 13 megahertz. That's that coil. The coil below is the coupling coil and is mounted on this truck. The truck's motorized, and we can work it from those buttons that we saw at the front and from here if we wish, to set it up to what position we need. The further it moves away, the less power is sucked out of the valves, and the closer it gets, the more power. So we can run up to 250 kilowatts in this position, and if we reverse it a little bit, we can run as low as about 100 kilowatts quite reliably. The RF passes then is now converted from a balanced system again to a balanced system. So balanced to balanced output, and it whizzes up through the arms here and then through the coils and capacitors inside this filter. This cuts any spurious off above 30 megahertz. It wends its way and eventually ends up on the 2 connections at the back there. You can see they're earthed down at the moment, they're open, they're not connected, and they're earthed down above so that we can work in here and not get pickup from other antennas on the field with senders radiating. So that's a broken connection to the outside world. When we shut the doors and lock it up, that becomes complete. And on the 2 connections at the top, they're the actual 320 ohms output balance feeder. There they are at the top there. And they take the power down the field in a balanced system. So that's a 250 kilowatt output RF stage. Let's go and have a look at the modulator now. Here we are in the modulator stage. You'll see an aluminium chassis there with a heatsink on it. That's a solid state audio amplifier. Replaced a leak audio amplifier from the 1960s. Remember, these were built in 1963, so obviously designed about 1961, 1962. And Marconi's used a leak TL12 plus amplifier for 5 valves, EF86, ECC81, a pair of EL84s, and a GZ34 to give 10 watts out into 2 100 ohm resistors on anti-phase. So you've got one phase one side and one phase for the other, We replaced the amplifier in the 1970s by, or 1980s actually, by a solid state one, because it was getting hard to source all the tubes by then. So that's the solid state amp then that drives the first audio, which is here, which is a TT21, a GEC tube, much used by Marconi's. That's capacity coupled. You can see some rather large capacitors. That's capacity coupled into the next stage, which is a pair this side of 813s. And if you just look to the rear, there's another pair on the other side. This is a push-pull amplifier. So this valve is replicated on the other side. The two 813s are over the other side. The 813s serve as a voltage amplifier. We want to get here a swing of voltage, about 1,000 volts, peak to peak. That's what we want from this stage. We want to drive the output valves hard. So to get that, with 1,000 volts of swing, but there is a slight complication when driving triodes. If you just look through, you can see the triode tube sat in the output there, exactly the same tube as used on the RF, BY1144L. However, to get the power out, we need to drive these valves in Class B. Class B normally involves grid current. But the poor old 813s can't deliver power. They can deliver voltage, but not power. So to get power, we need an intermediate stage. And here we have a pair this side of English electric valves, BY1654Fs, satin boilers again. You can see the steam take off here, and you can see the water input from the base. So we've got the cathode followers here then that convert the 1,000 volt swing from the 813s into a low impedance feed for these two output tubes. These can convert that feed to low impedance because we want to drive these things with power, or we want to drive them into grid current. There's a better view here on the modulator of the tube setup because it's more open. You can see the grid here attached by this ring. That's the actual grid connection. Best put it on. The filaments or the heaters are here on one side. That's one side of the connections, and here's the other. And there's air blast cooling from above to keep these connections cool. We've got the boiler again bolted down, and we've got this strange piece of fishing line here. This is called a heat fuse, and it's on the tube there, and it's solder that should the tube overheat, the solder will melt, and the spring here will pull that off, and the switch will shut, and that will turn off the high voltage on the transmitter. So it's a protection circuit against the water flow failing. This assembly here is a collection of capacitors and resistors, a ladder of them, a feedback ladder, and from one end of it is connected to the valve anode, the other end is connected to earth, but we just take a little fraction of the voltage from the far end and send it back to the front of the transmitter as negative feedback. And we run about 15 dBs negative feedback. 21 is possible, or 0. It's switchable at the front. So that's the negative feedback. You've got various suppression components in here, just like on the RF, except they're designed for audio. So that's the modulator. In a minute, go through to the modulation enclosure and see what's in there, but just to get in there, we need to gain access from this panel here. At the moment it is unlocked, but we need to get one of these keys out. These are called Castel keys. This one's got a number inside. It says 93 on it, etched, engraved inside. And it's such that when you put it in, it locks with the ident on the other side. So 93 fits with 93. You can't get 95 to go in there. I've already got a key here in the door. So we can open the door, go in through. And this is the sort of oily, smelly type area where the transformers live. The mains transformer, actually 2S, because there are two of them, are here. These take 11 kV, 11,000 volts AC from the national grid, and drop it down to about 10,000 or 9,000 volts. Two of them, and we feed the 9,000 volts or so via these copper bars here through to a solid state rectifier, which replaced a mercury arc rectifier. So it's a solid state rectifier just the other side of the door, which then generates the DC. So that's the mains transformers. The power from the modulator arrives, here's one of them coming in from one of the modulation anodes onto one terminal of the modulation transformer. Across here is the other, and there's a center tap where the 11 kV, 11,000 volts DC starts here. Notice we've got an earth wand on it. If you're watching in the States, it's a shorting stick in your country, but it's an earthing wand in the UK. It's often said that when transmitter staff retire, they hang up their earthing wand. That's one of the standard phrases. So that's the modulation transformer. Various bits of protection here, ball gaps for flashovers, and metrosils, which are like voltage-controlled resistors. Big voltage, it'll just shatter, but it will save the windings in the transformer. Just looking through here, we can see 3 large capacitors on the floor, a set of 3. These are modulation blocking capacitors, and are from one connection of the mod transformer to earth. The other connection up to the HT line is made by this reactor, which is here. It's always a reactor in the States, a choke in the UK. This is a low frequency reactor. It allows us to pass the DC through the reactor to the secondary of the mod transformer. The audio power gets superimposed on the DC, which then flows out to the tubes. The DC is prevented from flowing through the modulation transformer secondary by the capacitors on the ground. It's a standard way of doing it. If you just look through there, you'll see some more capacitors and some chokes, some smoothing chokes. There for the power supply smoothing for the regular 11,000 volt DC. We're looking to get 11,000 volts at about 50 or 60 amps. So we're looking for about a 600 kilowatts power load of HT at maximum modulation. You'll see some Jennings switches on the wall. These switch resistance mats out, inrush protection. There they are. Behind that and up to the high level is the air blast cooling department to generate the air that blows through the cubicles. And right above here we have one more vacuum switch with a large wire attached to it. It's got HT on one side, HV on one side, and a big fat green and yellow wire on the other. That's a crowbar switch that when we turn the transmitter off, that shorts out any HT that's left in the system. So that's the crowbar switch on the main HT. That's one you don't want to fail when it's running program. Okay, and so we've looked at the modulation enclosure. Let's just come out again and look at some of the coils that we use for the various frequencies. This is an anode coil here for the 9 megahertz band, 31 meter band. Looking down here, there's an anode coil for 21 megahertz band. It's behind the door. Collection of coils. Here's a coupling coil for 12 megahertz and an anode coil behind it with another one as well, both for 12 megahertz on the final stage. These heavier construction ones, here's a pen anode coil for 12 megahertz and a coupling coil into the final stage for 6 megahertz. Far more turns on that one. The ubiquitous stepped bar enables us to connect to a preset, a fixed coil that's already mounted in the transmitter for the lower frequencies for 9, 7, 6 and 4 megahertz. So that's that. It's in remote control at the moment. The light says so, so it must be. It's in remote control. I'm going to take it off remote and power it up manually. So let's take the HT off. Let's put it to local. This one's already on. So up we go. We've got relay supply, we've got the water coming up, it is already there, the air supply's on. Preamp's got its supplies, and we're just waiting now for the filaments to light. Let's wander around the side. I'll open it up so you can see the tubes on. We need to take the power supply off, or the HV power supply. We need to open the isolator. Wait for the motor to run through, and let's get some earths on. That gives me access to the key, or one of them. And if we open this door here, I have a good view of the valve fills. This is an old tube, an old style BUI 1144L, and it's got the glass body, and you can see the two heat fuses on this one, and you can see the fills up now. The cathode followers again, they're an old style of cathode follower, 3Z222EW, made by ST&C, replaced by the E2V ones, which are at the back there. But you can see the fills on inside the old girls there. Right, we'll shut this back up again so we can continue the power up. There you go. Earth's off. Motorised isolator shut. Power supply on. Thank you very much. Okay, off we come around the front then, see what we've got. That's a good sign. Okay, we've now got the fills on. The first AF, HT and bias is on. That's those TT21 tubes. They've got the supply. The aux HT's on. And we're ready. We haven't got an antenna on this one yet, so we can't progress any further until we do that. We'll go away and sort that in a moment, and then we'll have it on the air. We're now in one of the RIS transmitter fire cells. Not to work on the RIS transmitter, but to actually just a quick look at the control system, because we need to put an array, an antenna, on sender 95 so we can power it up for you. This is the manual part of the screen. And as you can see, we've asked for sender 95 to be there. It's on aux at the moment. It hasn't got any high voltage on it. It's going to be an AM amplitude modulation at 250,000 watts, 13.700, which you've seen before on the synthesizer. The antenna we're going to use is 953, and it's on a bearing of 75 degrees. Well, it will be when we enter all that information. When I press the send command, it will then, the information will go out, the switches in the antenna field will move, and we'll select array 953, put the bearing on 75 degrees, and it'll go on to sender 95. The right hand screen will show that for you. We've got the 10 senders available to us at Woofferton on the right hand side. The numerical order is not what you'd expect, but it's the way that they actually appear out of the building and then down the antenna field. This is an absolute picture of what it's like outside. So the most northerly switch station is 80, the most easterly switch station is transmitter is 84, and the most westerly is 92. But this is the way it's configured. So we're going to look at 95. Here are positions where switches are available. We run down here. There's another couple of switches down the end here. Let's just send this command then here, if I can find the here he is, if I can find send, and then we'll have a look at this side as 95 attempts to pick up an array. Thank you very much. As you see, it's now got a black line on it that goes to array 953 switch, and we follow that up and out it goes to array 953. The green circle indicates that everything is A-OK for power, so let's go outside now and put 95 on the air. Well, we join you again now. We've now got the antenna, array 953, it's got an interlock, it's on the front there. We're going to put the HT on this transmitter, the high voltage, and progress through to the HT is a normal value, and there's enough grid drive to light the modulator, to let the modulator pass audio power, and you'll be able to see that run up, and then you'll see me walk towards the sections and do the rest of the tune-up. So I'll put the HT on there. We've got a green, and if we just look at the top there, we've got the main HT at about 10.5 kV. Right, if I just progress now to the drive stage past the RF, this is ready to go on 13700. Press the HT. There we are. We've got about 3 kilowatts. 3 kilowatts on this frequency. Cathode current just under an amp. And as I say, the power is coming over the coax then into the RF section. Meters are fairly well balanced, you can see there. You've got meter readings here of balanced power. Final anode current, about 22 amps on this service. SWR 1.05 to 1, which is a pretty good figure to have. And the penultimate anode current just over about 4.5 amps. 4.5 amps, 11 kV, about 44 kilowatts in, so 30 kilowatts or so leaving this stage into there. Right, here we are then on the final stage. We're going to go for a manual tune-up now, so you'll be able to see the meters move and see what we have to do to tune the transmitter. It's actually tuned, but we'll give you a quick demo of how it works. So the pen stage first. Like most amps, min on the plate feeds, min on the anode feeds, max on the grids. Let's have a look. So pen stage, we're looking at this as the combined metering. I'm going to turn the controls now. Oh dear, didn't like that. As you were, keep it running. So that's the pen stage tuned, just over 4 amps. We're looking at the grid here now, just over 2. And we also look at the pen to see that they're balanced. If I just alter them slightly, just get them about the same. There we are. Nicely balanced. Grid's balanced, good. Look at the finals. Hands move down, eye moves to this meter combined. There we are, just dip at 22 amps. Look at the final stage here and set them both for the same value, just over there. So that's 22 amps, it's about 220 kilowatts. Want to run a bit more power, 250, just couple up to 26 amps. 26 amps, 250 kilowatts. 15 amps, 150 kilowatts. Easy. How much power would you like, sir? About 22 amps, 220 kilowatts. That's that done. Okay, well the cameraman zoomed inside now. We've put modulation on the sender. So you can see the cathode current now peaking, 5 to 10 amps or so. Just on the meter above it is the grid current. Just nibbles a little few milliamps there as the final stage runs into grid current. Just look now at the Orban. You'll be able to see the modulation on the front of the Orban Optimod unit. There we are. Here's the mod on the Orban, and you can see the gain reduction taking place on the various frequency bands. The bands are 160 Hz, 420, 700, 1.8 kilohertz, and 3.7 kilohertz. You can see the content of the program material. So that's the Orban working. And the transmitter working at 220 kilowatts on 13.7 megahertz. Not bad for 49 years old, since this was installed in 1963. Just look above here, we can see the number of hours that the machine has run. There's a meter at the top, it says 218970. That's 218,970 hours of program material. Quite amazing, really, in 49 years. Okay, so here we are continuing the tour at Woofferton. We've fast forwarded now from 1963. We're now in 1979, 1980, 1981, looking at the next generation of senders that was installed here. There are 4 units made by Marconi, type B6124. The previous 250s are BD272s. These are B6124s. 4 of them for the Voice of America, paid for by Ronald. He's a nice bloke. And totally different configuration to the previous system, as you'll see. It's like almost one continuous unit. We've opened a few doors for you. Got the RF section on the right hand side with a Rogue Orban Optimod unit in there. And on the left hand side is the actual RF section itself. We'll have a look at just a quick look at the front panel here, just to get an idea of what's involved. Frequency synthesizer again. These units have got 32 RF channels available. But look here, you can see we've got the 32 channels. We program those as humans to the frequency we want. Come down here, tune the sender up on power, tune it up, and then store the settings that we get. So they're manually set, and then it's able to remember the settings that we've put on as humans and drag them out whenever it wants to for the frequencies it does during the day and night. So these don't tune it from scratch. They have to be tuned manually and then stored. This is the unit that contains the 25 channels. and the tuning controls on the switches up and down with the readout display. As you see, this one's on 15620 kilohertz, and all the settings there are all stored. The servo control for the capacitors and one inductor. It's a roller inductor, servo control. So the sender's clever enough to know if it's 15 megahertz, it puts certain shorts on the coils inside, and this unit decides where the shorts go. Analog metering is provided. High level class B mod, or AB, it's in AB1, so grid current doesn't flow on the modulator tubes. They're around the corner, we'll have a look at those in a minute. So you've got the modulators here, and you've got the RF section metering sort of round the edge. Grid current, screen grid current, cathode current. Penultimate stage as well has got grid current, screen grid current, cathode current. We'll have a look at one of these working on a later shot. Again, the same sort of idea of indication of progress of transmission. Start with, is the mains present? Fairly basic. Then you go through the cooling and the filaments and the standby, aux HT, main HT, screen HT, transmitter on. But to get the yellows at the top here, you need to get the greens below. So have you got water? Have we got modulator water flow? Have we got RF water flow? High pressure air, low pressure air, black heat, filaments are energized, RF flowing through the components. All these supplies need to be on to progress to get the transmitter on the air. The overloads for the transmitter are here, and as I say, the all-band mod, the OptiMod unit is in the front here. The modulator driver is here, solid state, with a bit of analog metering. The two modulator valves just tucked round the corner. Let's have a look at those. Here they are. Thomson tubes, hyper-vaportron cooled. So cooling water in, hits the anode structure inside. It's ribbed all the way around, vertical ribs. Steam and water, or steam is made by the dissipation. A bubble of steam appears, and then the water goes in to kill the steam, take the heat away on the pipes there. A different system to the vapor system as on the older transmitters. Filament transformers below, and current metering, etc. in the middle there. So AB1, no grid current. A pair of tetrode amplifiers. Again, about 180 kilowatts, 200 kilowatts output. Very similar to the previous transmitter. Alright, this is the final RF stage above, and the pen multimate RF stage below on the 300 kilowatt B6124. The actual pen tube is located here in this little section, for its own little section. It's fed with drive from 150 watt solid state amplifier. Grounded cathode, and the anode circuit here is comprised of 22mm copper pipe with shorts on. These shorts can be pneumatically operated backwards and forwards. So obviously more coil in circuit, lower frequencies, less coil in circuit, higher frequencies. That's the switching for the pen. The pen drive then comes through and hits the grid of this final output stage. This is a 300 kilowatt output stage, again with a Thales tube. Tetrode, the 300 kilowatts is generated here. The drive for this comes from the pen, as I said, into the grid, and the anode circuit again is here. The tuning of the anode circuit is in two parts. We need to stop the RF going up the main HT power supply. So to do this, we have a parallel tuned circuit. Here's a Jennings capacitor and the Marconi inductor at the back. Here's a parallel tuned circuit. This is tuned to resonance on the carrier frequency. So the DC flows through the coil, but the RF has to flow down through the blocking capacitor here, down to the pi network, which is the output. So there's the pi blocking C, 1000 picofarads at 44 kV, that one. We'll go around and look at that stage in a minute. Okay, so here again is the pens. Here's the final stage here. Water-cooled capacitor, vacuum capacitor, ceramic body. That carries the full 300 kilowatts plus modulation to hit the output stage pi network, which starts here. And the first thing it finds is a motorized capacitor to earth. We blow the edges of these foils because the RF always wants to go down the edge, not among the whole foil, so it tends to fry the edges, so we blow those with air to keep them as cool as we can. There's at the back there is one of the shorts that's open, and that short would close on 26 and 21 megahertz, but it's open on this frequency, which is 15 megahertz. So the RF runs down through these 54mm copper pipes. Eventually, after going through a couple of pi sections, it ends up at the back here on this final run out from the bottom. Up it comes through the last two capacitors to earth, feeder load 1 and feeder load 2, and it hits the second harmonic tuned circuit. There's the capacitor. The coil fridge is on the right hand side, so we again resonate this and that tuned circuit for the second harmonic. The RF leads as an unbalanced output at 75 ohms through this aperture here, through a filter in the chassis work above us, a low pass filter to cut off all frequencies above 30 megahertz, and then up at 75 ohms into the enclosure at the top. This is a tuned palsy stub balun, 75 ohm input. It's a 4-to-1 transformer, so the output impedance is 300 ohms balanced, which is on the right hand side. So we get back to our balanced system to suit the arrays here at Woofferton. So that's a tuned palsy stub, 75 ohms input to 300 ohms output. Right, we've moved next door now from sender 82 to its brother, sender 84. This is one we've got set up for you so we can demonstrate it working. We've gone through the control circuitry, etc., and the servos. You can see now, looking at the Orban Optimog, we've got some program material coming in. See the metering kicking up, etc. We're on 11915 kilohertz, 11915 in the 25 meter band. Channel 17, it's labelled on this sender. What we're going to do is continue on from where we are on standby. If we just focus in now, you'll see that we've got the mains on, cooling, filaments, and we're up to standby. I'm going to make the main HT switch manually in a minute. That'll bring the aux HT on, the main HT, the screen HT, and the transmitter will come on the air. Then we'll have a look at the meters. It's okay, let's have a look here. The standby switches are already on, so I'm going to go now for HT start, and off we go. On this, you get a low power version, and then it comes up to full power. So if you just look at the cathode current meter, and you'll see it will come on at a low value to start with. Right, here we go on the switch. And up we go to 30 amps. 30 amps of cathode current on the final stage at 11 kV, about 300 kilowatts input. If we just look up here, we'll see we've got about 250 on the out. Forward power, 250 kilowatts. VSWR, about 1.09. And backward power, not a lot. So that's a good sign. Most things are working. Got modulation running. Grid current on the final stage, about 1.7 amps. Screen grid current, about 1.5 amps. Cathode current, 31 amps. We're driving from our wideband amplifier about 50 watts. Into the pen stage, there's the pen current, 1.4 amps. Pen screen, 40 milliamps. Pen grid, no grid current, that's quite normal. Got monitoring here of that bit of power, as I say, 50 watts from the drive. That's it really, not a lot else to tell you about that. You can see the modulation meters kicking with program.